Okay, so we're going to talk about something that's a little bit tricky, and it's activation energy. Now, at the very base, I think you guys understand that activation energy is the amount of energy required to make a reaction go. And it used to be believed that in order to make reactants go to products, first you have to break all of the reactants apart, and then you kind of had to put them all together again. And they discovered that the amount of energy that's required to do that was through the roof. So they came up with a different idea, that things started breaking apart while forming at the same time. And if you take a look at this diagram right here, you're going to see that what actually ends up happening is that this BRNO comes in contact with another BRNO. And what ends up happening is that right here, do you see how the two BRs, they start forming up just like the other NOs start breaking apart. So if you did it in pictorial form, if you take a look right here, you have these two BRNOs. And what ends up happening is they start forming the that's what the two blues are here, and it starts breaking apart over here, and you end up with the two independent things. Now, the amount of energy that's required to do that is called the activation energy. And this hump from the very bottom of this to the top right here, that's the activation energy. Now, if we can lower that activation energy in any way, the reaction will go more quickly. And that's one of the jobs that catalysts have, which we'll talk about a little bit later. Now, one of the things that we discovered is that when you increase temperature, you end up with more collisions that have enough energy to make a reaction go. So at a lower temperature, if you take a look here in the diagram, our T1 is lower. And if you see the number of molecules, the height of this is the number of molecules. It's hard, I'm using a new pen here. The height right here is the number of molecules or number of collisions at a particular point. And if you notice here, at a lower temperature, most of the collisions occur prior to the activation energy. So if you see down here, this is the activation energy, right? So the majority at a lower temperature are going to be occurring right here, and they don't have enough energy for the reaction to go. But if you increase the temperature, see how the curve kind of evens out, and you end up with more things that can react. So what we discovered, though, is that when we observed the things hitting into each other, we didn't have enough reactants with enough energy to cause the reactants to go. And part of the problem is that not only do reactants have to hit into each other with sufficient energy to react, but they also have to orient themselves in the correct way. So if I have two reactants like this, and right here they can't interact, and the only way they can interact is if they hit like this, then every collision, even if it has sufficient energy when it's hitting like this, will not do anything. It'll only react when you hit like this. So if you take a look at this diagram, it's delightful, and it shows the exact reaction here that we were just talking about. So if you have this, and they're arranged in this manner right here, do you see how the BRs can interact with each other, and they can form BR2, and then these two things can separate. Similarly here, if you have the BRs facing on with each other, they can interact with each other and form this. But if the O's come in contact with each other, nothing's going to happen because they don't have the correct orientation. So the reality is there's two things that we have to be aware of. One, that the collisions between reactants have to have sufficient energy. So one of the ways that we can increase the energy is by increasing temperature, causing particles to move more quickly, and they'll typically have enough energy to exceed or meet the activation energy. The second thing is they have to actually orient themselves in a correct way so they can react. Now, there's a really, really ugly equation. It's called the Arrhenius equation, and it's right here. And this is one that I would memorize if I were you. And actually, that one not so much, but the variation. And we are become huge fans of doing natural log of things. But if we do the natural log of Arrhenius' equation, we get an equation that relates the natural log of k to 1 over t. Now, again, ugly, ugly format, but if we remember our graphs, aren't they y equals mx plus b? And if we do that, we actually have a graphing format where the natural log of k is our y, negative e over r is our slope, 1 over t is our x, and our natural log of a is our b. Now, here's where it gets tricky, because our goal is this. They will often ask you in a problem, find the activation energy, right? And the way we've been doing it so far, it's hard to get from a graph. But if you plot the natural log of k versus 1 over t, you're going to get a straight line. And the slope of that straight line will allow us to figure out the activation energy. Now, this disclaimer I'm giving here is this. We're going to assume that all of the questions they're going to give us work with Arrhenius's equation, this equation right here, that they all work. There are some that won't. But I do want to point this out to you here, because if you look up here and we see negative EA over R, what we can say, and if we rearrange it, and it didn't, it should read here as equals. EA is equal to negative R of the slope. So again, that was not written very clearly, is equal to negative R times our slope. Now, and the slope is of the graph of natural log of K versus 1 over T. The other kind of weird thing is that our R is 8.3145. We'll just go with 8.3 joules per Kelvin mole. And if you remember back to our gas section, this is one of the gas constants. So we're actually using the gas constant here, which makes sense because a lot of the stuff we're doing deals with particles that are gaseous. But let me show you how this works in real life. So here's a reaction. N2O5, two of them hit into each other, and they form this stuff over here. Now, they will give you a table of K values and a table of temperature. And they'll say, calculate the value of EA for this reaction. So what we have to do then is that we have to switch this over so that we have the temperature. First of all, you can never do temperature in Celsius. Do we remember this from all our gas stuff? It always must be in Kelvin. So we're going to switch our temperature to Kelvin. Then what we're going to do is we're going to take 1 over T, because that has to be one of the axes. And then we're going to take our K, which they gave us up here, right? They gave us our K, and we're going to take the natural log of K. And so with our calculators and or something already done for us, we're going to plot the natural log of K versus 1 over T. Now, when we do that, we're going to get a straight line. Now, if you notice here, we can do rise over run to figure out our slope, right? And again, my pen is having all kinds of issues. So that would be the natural log of K over 1 over T, and that's going to give us our slope, which is negative 1.2 times 10 to the 4th. Now, once we have that, we can then go backwards from this. And remember, this is our slope right here, right? Natural log of K over the change of natural log of K. Again, this is rise over run. And we found that that was equal to negative 1.2 times 10 to the 4th Kelvin. This is the equation that relates slope and activation energy. So if we rearrange it, the activation energy is going to be equal to negative R slope, which again, if we remember up here, we hit that. Activation energy is negative R slope. So if we know what our slope is, which we do from our equation right here, 1.2 times 10 to the negative 4, and we know what our R is, we put a negative in front of it. It'd be negative 8.31. The 4.5 is not really necessary. Joules per Kelvin mole times negative 1.2 times 10 to the negative 4th, and the two negatives cancel out, and this ends up being our activation energy, 1.0 times 10 to the 5th joules per mole. To simplify this slope right here can only be gotten when we are using these two variables, natural log of K versus 1 over T. They may give you a table already done, or a graph already done, or they may give you a table that looks like this, and you're going to have to convert to natural log of K and 1 over T. Now, there is another way to do this without a graph. And this is one of these cases where we can just memorize, but if we rearrange, and there's a whole section on how we rearrange the equation, this natural log equation right here. If we rearrange it, we can end up with this right here, this ugliness. And what it allows us to do is that we can figure out the EA if we just know two temperatures and not the graph. So you have to know also the Ks, but if you arrange it here, T1, T2, K2, K1, you can then plug it into an equation and you can solve when there's just two variables. Now, there's a practice problem in the text. I'm not going to do a practice problem right here, but again, if you went back to our table that we just did, right, we could look at our K values here. Don't we have our K values here? And don't we have our temperature values? So what we could do is we could pick any two of our Ks and any two of our temperatures. Remember, it has to be converted to what? Kelvin. Right? We can never do Celsius, and we can plug them back into this equation, And it will allow us to solve for our EA just mathematically, even if we don't have a graph. So that saves us from having to plug in all the graphing points. The only way you're going to get this, because you're not going to derive it, is if you memorize this. Anyway, I know this is kind of a brutal section, but it is on the AP exam. Hopefully this has been helpful, and we're definitely going to practice in class. Thanks a lot. See you next time.